beta there? Because if it's just a basis change, it can be any arbitrary unitary matrix.
You mean in this context?
Yeah,
In this
yeah.
context, because we want to show that L star is related to this guy,
Oh.
right? You may not, you won't be able to do it for other epsilons, right? Because L star has a specific meaning. L star means in our case, C, e to the C, and then it's plus I beta, and then dotted into sigma star over 2, right? It's an explicit solution for your Lorentz boost in this SL2C form, and we got, how do we get here? Because we know L, right? L in turn was sigma, C, and then minus I beta, dotted into sigma over 2. How do we get here? We got here by explicit construction, right? And then in your homework, you're going to discover that C and theta really implements rotations and boosts in the way you think it would. Okay, so this is by explicit construction. But once you have a representation, you can take the complex conjugate and you will be guaranteed also a representation. Then the question is this equivalent to this? Okay, I didn't prove the statement, but the claim is that there is no such thing. There is no S such that S L star S inverse gives you back L. There's no such thing. Okay? And why is there no such thing? This is related to the fact that there is no P such that P sigma I, P inverse is minus sigma I. In fact, I should just write this as P. This S is actually related to P. Okay, so these two facts, I wrote it down previously, are related. And that's why we call them left and right-handed Weil spinors, because L and L star are not the same, but L star is related to L dagger inverse. So therefore, what we're doing right now is building our equations based off how they transform with respect to L and with respect to L dagger inverse. Right. So this is the left-handed guy. This is the right-handed guy. Right. Am I answering your question?
Okay, and next question is
Yeah.
From this question, it looks like the David beta relate to the gamma matrix in the Dirac equation.
We'll get that, but at this moment, not yet.
Oh.
Right? This one is 2 by 2 and one is 4 by 4. So not yet, but we'll get that. Yeah. Yeah. So what you will see is that sigma 2, when you put it in the Dirac, matrix form, gamma 2 is minus sigma 2 on this left, lower left corner, and sigma 2 on the upper right corner in the chiral basis or Weil basis. Okay. And then you will often see I sigma gamma 2. Then this will turn out to be like probably something like minus epsilon, something like that. I think plus or minus I sigma 2 is epsilon. So plus or minus, I forgot the sign, but basically, if you see gamma 2, they really mean epsilon as well. The generalization of that. Anyway, so let me continue this, and then we can build our Dirac equation. But am I answering your question?
I think yes.
Okay. Okay. All right. So again, we've discovered that. Let me write it down. Q prime mu is lambda mu nu, right? So under these transformations, the implementation of Lorentz transformations under these L's, that's what's going to happen to your momentum. And I'm just going to summarize. Q prime dotted into sigma bar acting on the transformed left-handed spinner is going to give you L dagger inverse acting on Q dot sigma bar acting on lambda. So this is left-handed, this is right-handed. I'm just summarizing what we wrote down because I want to use these guys and construct. Right. So again, so this is now right-handed. This guy is right-handed. This guy is left-handed. But the whole thing now transforms like left-handed. The whole thing here transforms like a right-handed one. So remember, the goal is to transform covariantly. So it better not be that we mix the left and right-handed objects, then it wouldn't transform covariantly. So for example, let's say I write down an equation that looks like this. Q dot sigma bar and then acting on lambda equals to, so we remember this whole thing transforms as a right-handed guy. So it better be, if it's equal to something, it better be equal to a right-handed guy as well, right? Or what is right-handed? It's rho itself, right? So this is left, again, this is left-handed. But after acting on it with Q dot sigma bar, we discover the whole thing now transforms like the right-handed guy. So it must be equal to, we must be able to write down in a covariant way that this is equals to something times rho. Well, there's something here, because I know that if this is momentum, remember that momentum goes like inverse length, right? In natural units, in units where C and H bar are 1, momentum goes like 1 over length. So this is dimensionless. This is just a bunch of dimensionless matrices. And L, lambda, and rho, you can assume they're both spinors, and you can assume they're both the same dimensions. So what I need here is something of dimensions 1 over length, or something of dimensions energy or momentum. Well, a natural candidate turns out to be the mass itself. Okay, so mass is momentum. Okay. So likewise, I can do a similar thing with Q dot sigma. By the way, I have a few typos in my notes. I'm sorry about that. So on Friday, I'm going to let you guys know once I've fixed my typos. Okay? Because I know you guys are doing the homework. So yeah, I'm going to check it through again by Friday and let you guys know. But so again, this is a right-handed guy, but we discovered that after acting on it with Q dot sigma, or whether you discover in your homework, you discover that this is now, the whole thing is now left-handed. So it better be equal to something that's left-handed, which is of course nothing but lambda itself. And the same logic holds that if you do dimensional analysis, it has this coefficient here must be of dimensions mass. And in fact, it is in fact mass itself. So far we've done it in momentum space. So now let me convert it to position space. How do I do that? I now view whenever I have something like that. For example, Q dot sigma bar acting on lambda. I now view it as instead sigma bar dotted into, with an I, a partial derivative acting on lambda tilde e to the minus I q dot x. Q dot x, by the way, means q mu x mu. right? So you can carry this out. So what is that? I sigma bar mu partial mu acting on lambda tilde depends on q but not on x, e to the minus q nu x nu. Okay? And when you differentiate it, I get I sigma bar mu, and I differentiate minus I q nu x nu lambda to the minus I q dot x. And when you differentiate this, you get exactly sigma bar mu, and then you have I canceling the minus I. When you differentiate this, you get exactly q mu. Okay, and that's exactly what we started out with over there. So as I've claimed, so what I'm claiming is that to go from momentum space, the argument of transformation properties is easier to make in momentum space. But now when you go back, if you want to go to position space, all it takes is to replace my q with I partial derivative. Right? So let me do that. Right? So what do we have? I have I sigma bar dotted into the partial derivative. By that I mean sigma bar mu partial mu acting on the left-handed guy must be equal to mass times rho, the right-handed guy. And then that guy, I will have I sigma dotted into partial derivative acting on rho, which then is equals to mass times the left-handed guy. Okay? So this set of equations transforms covariantly as right-handed, and this guy, this set of equations is left-handed. Okay? And now we can ask the question, now we can define parity in the following way. To be the following operation. I swap my left-handed and my right-handed spinors, and then I make the following transformation. X prime I is now minus that you want to build. If you want to build an equation that not only respects Lorentz invariance or Lorentz covariance, but also if you want it to be parity covariant. Okay, so in other words, if you switch left and right, and if you let x goes to minus x, you want the equation to take the same form. Okay, and so for example, this is a parity invariant equation, right? So for example, this is parity invariant. Right. What that means is that if you define your new y to be minus x, then you'll find that if you write the equation in terms of y, it takes exactly the same form. Okay. It takes exactly the same form. So let's do that. Yes.
Mix up with the parity and the rotation, because I remember that you have said for dimensions is odd, and rotations they cannot have parity invariant or something like that.
For rotations, we cannot have parity. Yeah, it's related to this. You're talking about this?
Yeah, I'm not sure whether this related to this part or not.
Yeah, I think it is. I don't know about odd part. If you can find me exactly where I wrote that down, we can talk more about it. But this statement is about the fact that left and right-handed spinners are related by parity, but there's no parity operator in this 2x2 context. There's no 2x2, I should have been more precise. There is no 2x2 parity operator such that P sigma I, P inverse gives you minus I. But I guess it's clear that it's 2x2 because sigma I is 2x2. But you see that if I do restrict myself to only rotations, then it is possible to find a change in basis from L to L star. So in that sense, the left and right-handed are related. But that's not what we mean in the full Lorentz group. Right? In the full Lorentz group, you will also have to include boost. And like I said, it's not possible to go from L to L star because you cannot find a change of basis. You can only do it when you are only considering boost, rotations and not boosts. I don't know if I'm answering your question. So let me say, if you can find me exactly where I said that, then I can tell you what's happening. But in this context, rotations can be mapped into rotations. So the left-handed rotations can be mapped into right-handed rotations, but not if you include boosts. Yeah.
I have a comment on that. Maybe you said that
Yeah.
in the even dimension, we cannot have the rotation. We can rotate into a parity. Which one?
Oh, I see. Oh, yeah, that's great. So what's the question? So yeah, that's true. So if you have even, so we can prove it explicitly that if you are in even dimensional space, then parity flips. By that I mean if you flip, every axis can always be performed through rotation. Yeah, that is true. Basically, you just rotate 180 degrees, right? The 2x2 case is the easiest to see. If you rotate by 180 degrees, you perform a parity flip. But then, if you are in odd space dimensions, like we are in, like we live in 3 dimensions, then if you let x1 go to minus x1, x2 go to minus x2, and then x3 goes to minus x3, you will find it is impossible to implement that through a rotation. That is true. But I'm not sure if I'm seeing what the question, how is it related to this? Is that what you're asking? But how is it related to our current discussion? What were you trying to ask? Meaning that fact is true, but I think you're trying to connect it to what we're saying here, but I don't quite see it.
So there's no relation?
Now you throw the question back to me.
I just cannot understand.
Yeah. So that's part. What can you not understand? Yeah, I'm not trying to make fun of you. No, I am genuinely trying to understand because I'm confused about what you're confused about. But if you tell me what you're confused about, try to clarify it. Yeah. Anyway, think about it. Okay, I'll let me continue, but stop me if you can phrase it in a sharper way, and then I'll try to answer your question. Okay. Let's continue. At least a little bit more. And then we'll take a break. So, oops, hang on. Yeah, so I think as part of your homework, that you're going to discover you're going to discover the following. You will discover the following property of, so remember L is not equivalent to L star. But you will discover that L minus 1 dagger is equivalent to L star. Okay, let me actually make sure. I think this is actually just what we just wrote down, right? So L star, remember, is epsilon e to the c minus I theta, and then dotted into sigma over 2 epsilon dagger, right? But this guy, I'm sorry, there's a class with a minus sign, right? But this guy is exactly what? If you take L dagger, you get e to the c plus I theta dotted into sigma over 2. Because these guys are all real, you flip the minus into plus, and sigma itself is Hermitian. So if you now take the inverse of this guy, then you see that all you have to do is you stick in the minus sign. So this will be e to the minus c plus I theta dotted into sigma over 2. So therefore L star is nothing but just epsilon L minus 1 dagger, epsilon dagger. So why am I saying this again? Because what you discover is that in the homework, you will discover that L minus 1 dagger, sigma bar mu, L inverse is sigma bar mu lambda mu mu. Okay. And remember that you've seen this a similar object before, which is that of sigma mu itself. Right? Remember that if you were using sigma mu itself, this would in fact give you sigma nu lambda nu mu. And so what you discover is that using these objects instead, you can sandwich them between, or rather sandwich sigma bar mu in between them, and you discover that that would also induce a Lorentz transformation. So this inverse, you can take it out, right? So this is an inverse. So you can immediately write down, if it were L dagger sigma bar mu, L, right? So which means I'm down doing the inverse transformation. That will give you what? It will give you actually lambda mu nu sigma bar nu. Okay, so I notice that this is now down up, and this is now up down, right? And why? Because this guy, remember, is the inverse of this, right? So lambda mu nu lambda mu alpha is Kronecker nu alpha, remember, right? So this is the inverse of that. And these two things would show up because this is exactly what happens in the Dirac equation. Okay. So let's summarize as follows. You will discover that the Dirac equation has the left-handed spinor, which will transform from one Lorentz frame to another through L dagger inverse, right? So L dagger inverse A, B, lambda B. Okay, that's one way. And if you are working with momentum, P mu will be lambda mu P mu. Right, so this would be a function of P prime, and this would be a function of P. Again, going from one reference frame to the other. If you have the right-handed spinner, then what we have is just, I'm sorry, this is the right-handed spinner. If you have the left-handed spinner, then you just have the usual so let me make sure my notes are not. Sorry, I meant to call this right-handed, so this should be row. I need to fix, this is a typo in my notes. This is row. And then the left-handed I call lambda. A of P is LAB prime prime lambda B of P. Okay. So we have to remember that these are the two basic transformation properties of the, again, right-handed and left-handed spinner. And we need to somehow combine them with these relationships to make sure that under space-time Lorentz transformations, the whole Dirac equation will transform appropriately. So what we should do is to go to momentum space and do this transformation, right? So what do I mean by that? So for example, what you're going to discover is that if you have an object that looks like the following, if you have sigma, if you have a Q nu, sigma bar nu, so this is a space-time vector contracted with sigma bar, and you act it on a left-handed spinner. But now you allow your left-handed spinner to undergo a boost, okay? And if you boost it, then you also want to boost your momentum. Then what will happen is that you will discover that this whole object, remember this is a matrix acting on a two-component spinner, and now you've boosted it, right? So this Q prime is lambda contracted with Q, and this is the Lorentz transform left-handed spinner, right? And what will happen is you will discover how does this object transform. It would in fact transform like Q in the X frame dotted into sigma bar, acting on the O spinner. This is the whole thing here is the Lorentz transform one. O spinner, but now the whole object will be acted upon by L dagger inverse. So you see a funny thing going on here. So let me just summarize what's going on here. This is a left-handed object. But once you have acted it up with this Q dotted into sigma bar, it now transforms like a right-handed object. Right? So this is a left-handed spinner. But after you act upon it, you find that this whole thing transforms as a right-handed object. remember the L dagger inverse or L inverse dagger. Remember you can swap the two symbols, right? L inverse dagger and L dagger inverse is the same thing. But this guy is in fact inequivalent to L, and in fact this guy is a right-handed transformation, this is a left-handed transformation. So just by acting your left-handed spinner on by this, your entire object transforms like a right-handed spinner. Okay, this is what you're going to discover in your homework. So I'm not going to do it. But likewise, and then we'll stop there. Likewise, if you do Q prime nu sigma nu acting on L dagger rho, you will discover that this will go by L inverse acting on Q nu sigma nu acting on rho. Or if you want to make it a bit more explicit, this will look like L in, not more explicit, but if you use the original left and right-handed guy, L inverse dagger acting on rho would make it L Q nu sigma nu rho, and then Q prime nu sigma nu. Okay. So again, this is a right-handed guy. But now if you contract it or act upon it using the boosted momentum dotted into sigma nu, not to be confused with the bar, right? There's a subtle difference here. This is sigma, this is sigma bar. But just by acting on it with this sigma nu dotted into Q prime, you discover the whole object now transforms as a left-handed object. Okay? So, left-handed guy, you act upon it with sigma bar, you get a right-handed guy. If you have a right-handed guy and you act upon it with sigma, you get a left-handed guy. So there must be some way you can combine these two equations to form one coherent set of equations for both the left and right-handed spinners. And that's what the Dirac equation is. Okay, so let me complete that after our break. Let's take a 10-minute break, and then I'll complete the construction after the break. Okay?